So this is question 2 of mock exam A. It starts off initially as a calculus question, and then it goes on to a tiny bit of CVAT just to balance things out. So using the substitution x equals tangent theta, show that the integral of 1 over 1 plus x squared is tan inverse of theta, or tan inverse of x rather. So this is a common result that you should actually know of by heart, but this is actually how you derive it. So we let x equal to tangent theta, and I'm just going to put here that theta is tan inverse of x. So when we differentiate this, we end up getting dx equals sec squared theta d theta. This becomes a dx by d theta, and then you multiply the d theta over. So then when we sum in our integral, we get 1 over 1 plus x, which is tangent theta squared, times by dx, which is now sec squared theta d theta. Now, another thing that you should know actually from projectiles is that if you have sine squared theta plus cosine squared theta equals 1, and you divide everything by cosine squared, you get tangent squared theta plus 1 equals 1 over cos is sec squared theta. It's really badly written. So we can actually write this then as just sec squared theta over sec squared theta d theta, which when those are cancelled, you just get theta plus c, the constant of integration. Now, of course, we know what theta is. It's tan inverse of x. So this is then equal to tan inverse of x plus c. Now, the next question I did kind of fumble. I've changed it in the actual exam paper, just not here on the OneNote. So hence find the area under this graph in x equals 1 and x equals 3 in terms of pi. Now, we know that the integral of this we've derived as tan inverse of x. So the area is actually just tan inverse of the first, which is root 3, minus tan inverse of the second, which is 1. Now, tan inverse root 3, if you think, is going to be a large angle, so I think it's pi over 3, but I will just double check here. Tan inverse root 3 is pi over 3, so that is pi over 3 minus tan inverse of 1 is pi over 4, and then pi over 3 minus pi over 4, I believe, is pi over 12. Yep. So that equals pi divided by 12 in units squared. And they want me in terms of pi, so there we go. Next, find the derivative of y equals cosec theta, where cosec theta is 1 over sine. Now, I did just throw the cosec bit in, this tiny bit here. I really should have a laser pointer, but I don't yet. I'll put it on for the next episode. Just because some people are actually familiar with sec squared anyway. Because when you differentiate tan, you get sec squared, and then of course sec squared comes in with 1 plus tan squared. Cosec is a bit of an annoying one, but still use it anyway. So we're trying to find the derivative. So y equals. Now there are actually two ways to do this. Either you can use the chain rule, or you can use the quotient. I'm going to use the quotient rule. So y dash equals the bottom times the derivative of the top, which is 0. Take away the top times the derivative of the bottom, which is cos theta. Just write that as cos theta divided by the bottom squared, which is sine squared theta. So this sine theta times 0 disappears, and this gets minus cos theta over sine theta times 1 over sine theta. That's just the way I'm going to write it. And mostly because when you actually type in the derivative of this, you actually get two trigonometric expressions not as quotients. So cos over sine is like 1 over sine over cos, which is 1 over tan, which gives you cot theta. This is negative cot theta, and 1 over sine we're told as cosec theta. And that's the derivative of cosec. Next, I don't know why I made this box bigger, but given that cot is 1 over tan, so that cosec squared is 1 plus cot squared. Well, we know that sine squared theta plus cosine squared theta equals 1. Now we want cosec, so we're going to be dividing by sine. So this gets 1 plus cos squared over sine squared, we know is still cot squared. And this is cosec squared theta, which is logically identical to cosec equals 1 plus cot squared. Now it's this little beast. Now a result like this is actually given in the log tables. However, if you're told to use the substitution here, then you should be using the substitution rather than quoting directly from the log tables. Essentially, that's what the whole question was about. It was about building the steps on how to actually evaluate this integral. So, x is cosec theta. Now we're told what the derivative is. We're told cosec is minus cot theta cosec theta, I think. Yeah, minus cot theta cosec theta, and this is d theta. Now, one thing with integration with substitution questions, sort of like this, when I think they're actually going to be more complicated, is I actually change the limits. So this is a common thing actually taught in A-level maths, but it's not necessarily done um, in any applied maths textbooks. However, it's probably best. So when you're going from the x world into the theta world, as black pen, red pen would say, you have to substitute in where we're told x is root 2. That implies that cosec theta equals root 2. Now, cosec is 1 over sine, so that would imply that sine theta is 1 over root 2, which we know is pi over 4. And then when x is 2, again, we get sine theta is 1 half, which means that, we'll call these theta 1 and theta 2, this is pi over 6. The sine increases for the acute angles, so when it hits a half before it hits root 3 over 2, and that's when it's pi over 6. So using the substitution and the dx, this is the integral of, I'll write the dx on top, as cosec squared theta times the square root of cosec squared theta minus 1 times by our dx substitution, which is negative cot theta cosec theta d theta, and is between pi over 6 and pi over 4. Oh, it's the other way around, because inverse function, so this is pi over 2 is on the top, so pi over 6 and pi over 4. Now, actually, a trick to do is if you multiply through by -1, the limits actually switch. And that actually helps with this negative sign here. So now we actually have the pi over 6 and the pi over 4 on the right side. Now, cosec squared theta minus 1 we can quote from here as cot squared, because if you move the 1 over, we get that cot squared theta is actually cosec squared theta minus 1. So this is dx all over cosec squared theta times cosec squared theta minus 1. We know it was cot squared theta, so the square root of that is just cot theta times by cot theta cosec theta d theta. So the cot cancels with that cot, and we get a cosec cancelling with that. Now, 1 over cosec is 1 over 1 over sine, which just leaves us with the integral of pi over 6 to pi over 4 of sine theta d theta. Now we can actually evaluate instead of chucking, say, sine of cosec theta in. So sine integrates to minus cos, and we're evaluating this between pi over 6 and pi over 4. So because cos is decreasing, this actually makes a lot of sense. So it's actually cos of pi over 4, which is 1 over root 2, and then cos of pi over 6, I think, well, that's actually going to be plus square root of 3 over 2. And this becomes root 2 over 2. I should have actually wrote that as root 2 over 2 instead. And then, sort of, when we simplify this, we can factor it a half and we get root 2 plus root 3, which is the area of this thing here. No, minute. Whoops. I was just looking at it because that answer doesn't look familiar. So I did it went too fast there. So you have minus cos pi over 4 plus. Missing a minus sign. So this is still root 3 over 2, and this is still root 2 over 2. But we can write this as root 3 over 2 minus root 2 over 2, which is 1/2 of root 3 minus root 2. That looks a bit better. Uh, I will actually have to double check because I did this integral before, and that looks like the right answer. So I'll just be a couple minutes just trying to get up the original source of this integral, which some of you might have spotted already, but I will still just check. Uh, yeah, 1/2 of root 2 minus root 2. Perfect. So that's that question done. It's a lot of work, but if you know your trig stuff, then you should be okay. Now, a bit of a breather here. Car accelerates from rest to speed of 20, so even before anything, Suvat. Why those dots keep appearing? So from rest, speed 20. That's all we're told. Time spent at constant velocity. Okay, so we're going to actually save this for later. So 1.2 kilometers is the distance at constant speed. So the distance is 1,200, and the speed is 20. So this is just time is distance over speed, which I think is 60 seconds. Yeah. So 60 seconds. If the total distance traveled is 2 kilometers, find the ratio of the acceleration to the deceleration. Okay. So we're told that it's 1.2 at constant, then it's 500 decelerating, plus some mystery distance. That's 2,000. So that's 1,700. So we know that the distance traveled accelerating is 300. So a Suvat table for the acceleration. We know that it traveled 300. It started from rest. The acceleration we don't know. And we have the speed is 20. So we get that v squared is u squared plus 2as. So that's going to be 400 is 0 plus 2a by 300, so 600a. So a is 400, 600, 2/3. So I'm going to call this a plus. Now to find a minus, the time spent decelerating was 500. Distance spent. The initial speed is 20, goes to rest, and we want to find a minus. So again, we use v squared. So it's 0 is 400. Let's go outside of the borders here. 1000 a. So that would be minus 2/5. 400, 4 over 10 is 2 over 5. Yeah. So that's a minus. Now, acceleration to the deceleration is 2/3 divided by 2/5. So we're taking the magnitude here. So we do, oops, 2/3 divided by 2/5. The ratio is 5/3. So the acceleration to the deceleration is in the ratio of 5 to 3.